Welcome to today's explainer. Look, if you're a prospective engineering student or maybe a parent trying to help your kid navigate the incredibly crowded world of higher education, you are in exactly the right place. Consider me your personal industry mentor today. We're going to uncover a branch of engineering that's rapidly becoming one of the most future-proof, highly lucrative, and globally demanded career paths out there: Instrumentation and Control Engineering. To really grasp why this field is just absolutely exploding right now, I want you to ask yourself a simple question. Who builds the nervous system of a smart factory? Think about it like this. If mechanical engineers build the muscles, the heavy machinery and the robotics, and software engineers build the brain, the code and the algorithms, then instrumentation and control, or IC engineers, they build the vital nervous system. They create this incredibly intricate network of sensors and feedback loops that lets the brain actually talk to the muscles and control them in real time. Without IC engineers, modern industry is literally paralyzed. All right, let's dive right in. Here's our roadmap for this explainer. We'll cover Industry 4.0's nervous system, your academic roadmap, career stability versus software, real-world impact, and finally, we'll talk about those global salaries. Starting off with Section 1, Industry 4.0's nervous system. Right now, the entire global industrial landscape is undergoing a massive, profound transformation. Traditional manufacturing jobs are shifting fast, and modern facilities are just desperate for experts who know how to automate complex physical processes. You're going to hear the term Industry 4.0 thrown around a lot. Well, at its core, it's driven by cyber-physical systems. And as an ICE engineer, you are right at the absolute center of this revolution. You're the architect, designing these integrated networks of smart sensors and actuators. You're building the systems that grab real-time data, process it instantly, monitor the heavy machinery, and catch anomalies way before a human eye ever could. So you literally bridge the gap between physical processes and the digital world. This degree perfectly positions you to handle the absolute cutting edge of manufacturing. We're talking about setting up predictive maintenance, where AI actually tells you a machine is going to fail before it happens. You'll be running digital twins to safely simulate factory changes, and even facilitating human-machine collaboration, where operators work seamlessly right alongside smart robots. It's really wild stuff. Moving along to Section 2, your ICE academic roadmap. Okay, let's be real for a second. Getting this degree is an intense 4-year journey, but man, the rewards are so worth it. Let's break down the syllabus a bit. After you get through your general engineering foundation in year 1, the real fun kicks in. Year 2 is all about foundational circuitry and transducers, basically learning how to take physical reality, like heat or pressure, and turn it into electrical signals. Then, year 3 ramps up into advanced control, process automation, and programming those complex industrial computers we call PLCs. Finally, in year 4, you get to customize your path with advanced specializations and tackle a massive hands-on capstone project. Now, what's really interesting about this slide is just the incredible breadth of final year elective courses available. You aren't boxed into one tiny corner at all. You want to specialize in the industrial Internet of Things? Go for it. Robotics and automation? Biomedical instrumentation? Aerospace? You can literally take your career in almost any direction you choose. But hey, to get to those exciting electives, you gotta survive the core classes first. The top survival advice straight from successful students and industry mentors is pretty simple. Master your math and circuit foundations early on. Control theory is mathematically rigorous. You absolutely need to understand differential equations and operational amplifier design inside and out. Why? Because when you're working in a super noisy, high-voltage industrial plant, you have to ensure those delicate sensor signals aren't getting corrupted by electrical interference. All right, Section 3, career stability versus software roles. Now, this right here is a major point of conflict for students and parents right now. Do you choose a core engineering branch, or do you jump into computer science? Let's look at the reality of today's market. We all know the allure of IT and software. The starting salaries can look really flashy, but software-only careers are getting incredibly volatile. We're seeing high market saturation and severe tech layoff risks everywhere. Compare that to instrumentation and control. It is rock solid. Automated chemical plants, oil refineries, municipal water grids, they require physical, on-site maintenance and continuous upgrades. You can't just turn off a power plant because the market dipped. The essential nature of physical automation gives you unparalleled job security. Plus, IC graduates hold what I like to call the ultimate jack-of-all-trades advantage. Because you intimately understand both the hardware machinery and the software code running it, you're incredibly agile. If traditional heavy manufacturing slows down, no problem. You can pivot into developing software-based automation tools. Or even better, you can seamlessly transition into the booming renewable energy sector, designing the advanced instrumentation needed to manage these massive, modernized smart grids. Which brings us to Section 4. Real-world impact and ethics. You know, this career isn't just about the money or the job security, it's about real, tangible global impact. You aren't just pushing pixels around, you're ensuring global safety. And this brilliantly illustrates exactly what we're talking about. Take a fully automated candy factory, for example. ICE engineers design the entire loop. First is sensing. You use load cells to weigh the sugar and thermal detectors for the exact boiling points. Second is control, using PLCs to instantly calculate any needed adjustments. And third is actuation, automatically tweaking pneumatic steam valves to keep temperatures absolutely perfect. This automation minimizes human error, stops ingredient waste, and guarantees that every batch is perfectly consistent. But the stakes get a whole lot higher than just candy. Imagine designing the systems for a colossal hydroelectric power plant. You're managing immense, terrifying physical forces. IC engineers use advanced SCADA systems to constantly monitor water pressure and turbine vibrations from a centralized command room. If a sudden pressure drop happens, those safety instrumented systems that you designed will automatically shut down the water intake. You're preventing catastrophic structural damage, and potentially you're saving lives. Or think about the biomedical field. IC engineers are absolute lifesavers in healthcare, literally bridging the gap between electronic hardware and the human body. Think about a heart monitor. The electrical signals from a human heart are exceptionally weak, right? And they're easily corrupted by all the electrical noise buzzing around a hospital room. IC engineers are the ones who design the signal conditioning filters that strip away that noise. That ensures accurate diagnostics and absolute patient safety. Okay, on to our final segment, Section 5, Salaries and Global Opportunities. So the work is fascinating, it's essential, it's highly impactful, but I know what you're thinking. Let's look at the hard numbers. Check out these phenomenal placement stats from NIT Trichy, one of India's premier institutes. The Instrumentation and Control Department placed an incredible 81.58% of its batch. That outpaced computer science at 76.92% and mechanical at 69.47%. Why? Because ICE graduates are highly competitive for both core industrial roles and software IT roles. You get the best of both worlds. So, the crucial point here is the financial trajectory. In India, a fresh grad can expect anywhere from 2 to 4 lakhs per annum, but as you gain specialized experience, that jumps to around 8 LPA within 3 to 8 years. And seasoned professionals with over a decade of experience, they are regularly pulling in upwards of 21 lakhs per annum. And we're talking about getting hired by global heavyweights like Honeywell, ABB, and Reliance Industries. And listen, the demand absolutely does not stop at the border. There is a massive global talent gap right now. Senior engineers are retiring, and the whole world is rapidly shifting toward automated manufacturing and renewable energy grids. Hotspots include the US, which needs you for energy infrastructure, Canada, heavily investing in oil, renewables, and wastewater, and Germany, which is practically starving for automation experts to run their world-leading automotive and robotics sectors. To put a specific number on that global potential, $164,000 to $850. That is the peak average salary for an ICO engineer working in specialized U.S. nuclear power hubs like Mineral, Virginia. The financial return on investment from mastering this complex interdisciplinary degree is simply immense. Which brings us to my final question for you. If you want a career that bridges software and physical reality, offers ironclad job security in an increasingly automated world, pays exceptionally well, and directly impacts global safety and sustainability, are you ready to choose Instrumentation and Control Engineering? The future is completely automated, and it desperately needs a nervous system. Will you be the one to build it? Think about it. Thanks so much for joining me on this explainer, and I'll see you next time.